Hello everyone. Today we're going to be talking about flywheels. This is a continuation of force analysis. Also talk a little bit about the project that's going to be due a week from Friday. That'll be an engine force analysis. So it's something that I haven't really tested or had a homework over. So it'll be kind of like a big homework assignment essentially, the project. All right, so shaking forces is the first thing I need to talk about. So when you've got something like an engine here, so we've got a crankshaft, we got a connecting rod, we got a piston here. As this thing rotates, so as this rotates, the parts inside are going to be moving around. So the centers of mass inside this are going to be moving around. So if you remember back from dynamics and the whole equal and opposite reaction thing, if I've got a center of mass that's moving, say, I'll actually be moving like, run perpendicular, be moving somewhere like that. If the center of mass is moving that way, then the machine it's connected to is going to be moved in the opposite direction, right? The equal and opposite force is going to act on the ground. And if the connecting rod here, center mass is moving that way, then it's going to try to make the thing it's connected to, the engine block in this case, move in the opposite direction. So essentially all the masses that are being slung around inside the engine, the equal and opposite reaction is going to happen on the engine block itself. And so that's what we're talking about with shaking forces. It's the equal and opposite of the forces acting on the mechanism to drive the mechanism. So when we did the force analysis for this, when we looked at the free body diagram for the crank, we had this force F21 that was the force from the ground onto the crank. So the shaking force of that would be the equal and opposite. So it would be the force from the crank onto the ground, which would be the engine block. We had this F4-1, which was the force from the wall of the piston, or the wall of the cylinder, on the piston. The equal and opposite would be the force that the cylinder wall exerts, the force that the piston exerts on the wall of the cylinder. So the sum of those two forces would be the net force that the block would be experiencing. So that would be the force that would go to accelerate the block of the engine. The shaking moment is going to be the moment due to those two forces. And it's also going to be the opposite of the moment exerted on the crank. So there was the moment required to drive the crank, given us a specific set of kinematics. The equal and opposite of that would be part of the shaking moment. Now, remember, for moments, you have to pick a point. So here we're going to sum moments about the center line of the crankshaft, but you could sum them about any point you need to. So the sum of the shaking forces, that's going to be the total shaking force on the ground. Some of the moments, that's going to be the shaking moment on the ground. So essentially what we're doing is we're doing a free body diagram of the ground and finding all of the forces and moments that act on the ground, and that will be the shaking forces and moments. So I'll put a link to this video so you don't have to type this whole thing out. I highly recommend you watch this video. So pause this right now, watch this video, and then come back in a few minutes. I really like this video. Students think this is hilarious. I don't know. It's a good video. So I wish I could just show it in this, but copyright sucks. So anyway, I highly recommend you watch that video and then come back to the slides. So yeah, and again, that was shaking forces at work for those of you that did watch the video. If you didn't watch the video, go back and watch the video. But shaking forces can be very significant. And when we start talking about engines and balancing, it's a big deal. It's a huge deal. So we'll talk more about that when we get to balancing. For now, what I want to talk about is dealing with this component right here. And that there's a very specific way to deal with. These other things, balancing is how I reduce the forces. But to reduce this, we use flywheels. So that's mainly what we're going to be talking about today. We're going to be talking about flywheels. So this is a plot of that torque, that T2-1. So this would be the torque on the crankshaft of an engine just to spin the engine around at a constant speed. So the engine's not doing any work. It's not really doing anything. The piston's just going up and down. The crank is spinning. The connecting rod's doing its complex plane motion. And this is the torque required to drive it at a constant RPM. And I forgot to plot it at 360, so it closes over here at 360 and does a nice loop after that. But here we need 800, I believe this is pound-feet of torque required to spin this small single-cylinder engine at, can't remember what the RPM is. 3,600 RPM is what this one's spinning at. So for this, and I modeled this on a relatively small single-cylinder engine. This is going to be very similar to your project. Just doing one of these data points essentially is what your project is, not the whole plot. But just doing force analysis at one day, or for the full sweep of an engine here, small single-cylinder engine at 3,600 RPM, it takes almost 800 pound-feet of torque at this instant to get this engine to turn at a constant angular velocity. So it's hard to explain, but what this means is that the engine isn't spinning at a constant angular velocity. So for one cycle from 0 to 360 degrees of the crank, so I need instantaneously 800 pound-feet of torque here. I need instantaneously negative 800 pound-feet of torque. And if the engine's not connected to anything, there's no source for that torque. So what happens? Well, what happens is when I need torque and I can't get it, the engine slows down. And then when I need to put torque out and there's no place to put it, the engine speeds up. So it's this torque demand curve here, since it can't be met in most cases. What ends up happening is the angular velocity of the engine's not constant, and so it'd be continuously speeding up or slowing down through a cycle, assuming no friction losses. If you spin an engine up to some RPM and then you don't have it connected to nothing, no friction losses, no pumping losses, anything like that, then you'll see the crankshaft will be speeding up and slowing down continuously. And this is all happening in a cycle. So at 3,600 RPM, that's 60 hertz, so 60 times a second. So this curve is happening in a 60th of a second. So you get really big vibrations. So this would be a 60 hertz vibration. This has got some second order harmonics in it. We'll talk about that later on. But the main trend here is basically at the frequency that it's running at. And so essentially what that means is the crankshaft of this thing is going to be shaking at about 60 hertz. And if you have no idea what 60 hertz is like, if you've ever heard like a transformer buzzing, or another piece of electrical equipment buzzing here in the U.S., they almost always buzz at 60 hertz because that's the frequency that our electricity runs at here. It's 50 hertz in other places. But at 60 hertz is a very typical buzz that you're probably hearing right now if you start paying attention. I'm sorry if that's going to drive you crazy. But if you're ever around a big transformer or something and hear it buzzing, it's buzzing at 60 hertz. So in this case, this engine, the torque, there's a 60 hertz torque ripple and speed ripple on the crank in this. So what we want to do is we want to squish this down and make it better and reduce those vibrations and that torque and speed ripple. So that's really what we're doing with Flywheels, is we're squishing this required input torque graph down, or making it run smoother. And you see this on all sorts of engines, especially big single-cylinder engines. The bigger the mass of like the piston, the connecting rod, the crank, the bigger of a problem this is going to be. And usually, if you think about multi-cylinder engines, with a multi-cylinder engine, you're, for the same amount of displacement, you've got twice as many components, but they're smaller components, and the sum of the effects sort of cancel each other out, and it becomes less of a deal as you get more and more cylinders for the same displacement. This becomes less of a problem. But for big single-cylinder engines like this big steam engine here, it's a huge problem, and so you need an absolutely gigantic flywheel to solve this torque ripple problem. So what would happen if you didn't have this flywheel? If the engine would run at all, it would be super jerky. And in some cases, if it has no flywheel, an engine just won't run. It's not able to store energy to get through compression on a 4-cycle engine or a two-stroke engine. You got to have some energy stored up to get through compression. On a single-cylinder engine, where you've got a power stroke, you got an intake, intake, compression, power, exhaust. The only time you actually get any work is from the power stroke. The other 3 strokes all require work, and you need some place to store energy from the power stroke for those other strokes. And that's the flywheel, the mass of the vehicle it's connected to. Those things all are part of that system. So, but in this case, for an engine like this, it probably wouldn't run, and if it did run, it would run very jerky, and it wouldn't work very well without the flywheel. So the best way to think of a flywheel is it's a torque averaging device. So And this is true when you think about like small gas engines, like a small 5-horse Briggs and Stratton engine or something like that, a small gas engine. If you look at those, they've got a big flywheel on them. They've got a big, usually big chunk of cast aluminum that serves a lot of purposes, but it's a flywheel for the crank. Usually also is a fan for an air-cooled single-cylinder engine, and it's also the ignition timing system. It'll have a little magneto. It'll have a magnet that's spinning on it. There'll be a magneto that the magnet goes past, and that causes a spark. So there's a lot of functions, but its biggest one, and the reason it's so big and heavy, is because it's a flywheel for the engine. It'd be fun to try to run one of those without that. You'd have to rig up a separate ignition system for it and cooling, but I've never tried that. And again, if it even runs at all, it's going to run very jerkily. Torque averaging, this works by storing and supplying energy. That's essentially what we're doing. Is when we have excess energy, we put it in the flywheel. When we need energy, we take it from the flywheel. So it's a mechanical battery. So the math on this starts out pretty bad, but it actually ends up in a pretty simple place. It's a pretty simple technique for sizing a flywheel. So I'll get through the derivation here, and we'll talk about how you actually apply this for a couple of examples here in a second. So energy for a rotating body is 1/2 I omega squared. Torque summation for the system, that's easy. Sum of torques is I times alpha. So we're going to separate the torque required for the load and the torque required to drive the load. We're just doing that really those aren't really separate things, but we're going to separate them for the case of this. Essentially what we want is the torque required to drive this thing to be equal to the average of TL. So we're going to go ahead and substitute T average in. We need to do a little bit of kinematics here. We're going to get rid of alpha. Since we're dealing with energy, we need to get this in terms of displacement. So alpha is d omega dt. We're going to multiply top and bottom by d theta. We're going to flip these guys here. And note that d theta dt is omega, so we can replace alpha with d omega d theta times omega. So we're going to go ahead and replace that. We're going to multiply both sides by d theta here, separation of variables. We're going to integrate, and we get this equation here that relates the work done from the angle at the minimum angular velocity to the maximum angular velocity. Will be our bounds of integration. Will be from the minimum angular velocity to the maximum. So that would be, for a cycle, the minimum angular speed to the maximum angular speed is what our limits of integration are. So they're going to be in terms of this omega here. So omega max to omega min, and then since our variable's theta over here, we're integrating with respect to, we need theta at omega max to theta at omega min, and we're going to relate that here to this change in energy. So work done, change in energy, right? It's just work energy. So consequences of this, the flywheel is going to be speeding up or slowing down as work. So if when we have excess work, the flywheel speeds up, omega changes. When we need work, the flywheel slows down. What this means is it's impossible to get a constant angular speed. For any mechanism that has any kind of torque ripple on it, I can make it better by putting a bigger flywheel on it, but to get the torque to be closer to the average, I always have to be speeding up or slowing down the flywheel. So I can never do a perfect job of this. I can just do a good enough job. Okay, we're going to define torque fluctuation as the difference between the maximum and minimum angular speed of the flywheel through a cycle. Define coefficient of fluctuation. That's going to be the fluctuation divided by the average speed. That's essentially a percent fluctuation of speed that's allowed. And this is going to be one of our design parameters. So we'll select an acceptable value of K, say a 10% torque ripple will be allowed, or speed ripple will be allowed, and then we'll solve for the flywheel required to accomplish that. So to do that, we need to find this work done. So we need a reliable way of finding that work done, and I'll give you that here in a second. That's equal to our energy. We're going to rearrange our energy and get that in terms of our coefficient of fluctuation. That's pretty simple to do. We're going to factor that out into two terms. We're going to replace this term with the omega average. So if we assume it's a simple harmonic motion, which is not a great assumption, but it works okay for this, Then we can replace the average angular velocity with the sum of the max and min divided by 2. So we're going to replace this with 2 times omega average. This we've already defined as fluctuation. So this equation, the energy side becomes 1/2 I fluctuation times 2 times omega average. We can take this equation up here. We can move omega average to this side. We can replace fluctuation with K times omega average. So we replaced fluctuation with K times omega average. And we get a 1/2 and a 2 that cancel out. So we've got E K omega average squared. We can solve this for I, the required moment of inertia of the flywheel, by dividing by everything else over here, and we get flywheel sizing. We need the energy, so we need to solve this integral here, which that's what I'll talk about in a second. We need our desired coefficient of fluctuation and our average angular velocity for a cycle. And again, it's a lot of derivation to get here, but the end result's not bad. This is my equation for flywheel sizing, and I need a way of evaluating this integral. So that is the integral from of the torque required to drive the thing minus the average torque from the angle at the minimum angular velocity to the angle at the maximum angular velocity. So I need to figure out what those boundary conditions look like. So let's do that for a simple example first, and then I'll do it for a different example that's got a non-zero torque average. So this is the integral we're evaluating, TL minus T average. So there's a couple different cases that you might encounter. The first is when T average is equal to 0. So that's going to be for like the engine that's running with no friction, no pumping losses. It's not connected to anything. You know, in a perfect world, it would sit there and spin at a more or less constant angular velocity forever. At least the average angular velocity would be constant. So for any machine where it's not doing any work, we're not putting any work into it, in that case, this T average would be 0, and we're just evaluating the integral of TL. So this first example here will be for when I integrate this energy, when I integrate the torque output over 360 degrees here, if the total work done is 0 and the average torque is 0, then that'll be this example here. So if you look at these numbers here, they all add up basically to 0 at the end of this. So what is this? What are these numbers? This is work done. So this is the torque output for this engine, plotted as a function over a displacement, 360 degrees here. So note on units, this is pound-feet of torque is what this chart is. Remember, foot-pounds is the unit of energy in crazy US units. So how do I get pound-feet to foot-pounds? I need to multiply torque times theta, where this is in pound-feet times radians, not degrees. And then I get foot-pounds of energy. For those of you that are used to metric, I'm sorry. But that's what we got to do. It kind of works like that in metric. It's got to be Newton meters times radians, and they just have a named unit, the joule. We should have a named unit for energy here in the US. I don't know why we don't. But anyway, that's what happens here is we're going to integrate this graph, foot-pounds, and this 360. I plotted it in degrees because that's easier to get your head around. But when we do the math internally, we need to do radians for this. So this is the area under this curve where I use the angle in radians. So in this case, this is all given. Where did I get this? I plotted this all out in Excel and then did a numerical, did a trapezoid rule here to find the area of each of these little pulses, assuming it's a little trapezoid. Dang it, no, I don't want to do that. Sorry about that. The stupid thing kicked me out. Okay. So anyway, I did a numerical approximation using a trapezoid rule to find this area under the curve. So that's how you do it if you're actually plotting this in like a computer program or a spreadsheet or something. For this class, I'll usually give you the areas or give you something that you can reasonably calculate the areas. Okay, so how do we find the energy accumulated from the minimum angular speed to the maximum angular speed in a cycle? So uh, here we've got, sorry, excuse me. So here we've got this curve. It's negative, it's positive, it's negative, it's positive. So we find all the zero crossings. Stop doing that. So here's all the zero crossings. So this is torque output. So when this is negative here, that means to stay at a constant speed, it needs torque. Here it's positive, so to stay at a constant speed, it needs to deliver torque. Here it's negative, so that means it needs to be receiving torque. Here it needs to be giving torque. So here sorry about that. I took a little bit of a break and paused, and I'll cut these two together. So anyway, we've got, let me get my pen going. Here we go. So when the work done is positive here, when the torque out is positive and the work being done is positive, it's going to be delivering work. When it's delivering work, it's going to be slowing down to deliver that work. So when this is positive, it's going to be slowing down. When it's negative, it's receiving work and it's going to be speeding up. So we need where it's at its slowest and at its fastest. So where it's going to be at its slowest is when it has done the most work. Where it's going to be fastest is where it's received the most work. So what we can do is find all the zero crossings here, find the area of each of these pulses, and then find the sum at each of the zero crossings. So we have a negative 190 foot-pounds there, so it's been speeding up because work's going into it. It's going to get here and it's going to start to slow down. And we find the area at C where it's done 883 total foot-pounds, and it's going to be slowed down because it's doing work. Here it's going to start speeding back up again, and then here it's going to start slowing down. So if we look at the total accumulated area, so from A to B, it's this. From B to C, it's, sorry, this is A to B, B to C, C to D, D to E. This is A to B, this is A to C, this is A to D, this is A to E. So these numbers are the total, the sum of this column, the running sum of this column. And so that's the total energy accumulated at each of these points. So at B, there's negative 190 foot-pounds of energy. At C, there's 693. At D, there's negative 197. Over at E, there's negative 10 foot-pounds. So what we want to find is where it's going to be at its slowest. It's going to be where it's done the most work. It's done the most work there. Where it's going to be at its fastest is where it's received the most work. So it's received the most work here. So essentially, in the sum column, we're looking at the most positive and the most negative numbers. So the most positive will be the minimum speed, the most negative will be the maximum. Here they occur after each other, but note that it almost occurred in this first pulse here. So these can occur anywhere, they don't have to be in order. We're looking for the biggest and the smallest numbers here. The integral we're trying to evaluate, this integral here, is going to be the sum of the most positive and most negative. So we're going to find the sum of these two. So I shouldn't say the sum of these two. What we're really trying to find is the absolute magnitude between these, the difference between these. So there's different ways you can do it. You could take the absolute value of each of these and add it, or you can take the positive one and subtract off the negative one, or you could take the negative one and subtract off the positive one. Either way you do it, you're going to get the sum of the absolute value of these things, which is 890 foot-pounds of energy. So take these two numbers, the biggest one and the smallest one, absolute value, and add. That's the energy that you need, 890 foot-pounds in this case. That's what's going to go into the flywheel sizing equation. So we put that in for our energy. For this example, we're going to use a 5% coefficient of fluctuation. So a 5% coefficient of fluctuation, we need the average speed. So in this case, we're at 3,600 RPM, convert to radians per second, and my units are going to work out here if I've got foot-pounds and radians per second. So from this I can calculate the size of the flywheel required, the moment of inertia for the flywheel. So in that case I end up getting, you can see the units working out here, I get 0.125 slug feet squared for the flywheel inertia. From that I can then select a shape. So for a disc, I is 1/2 mr squared. I can select a radius of 3 inches, which would be 1/4 of a feet. I need to get my units to work out here, so I need slugs for mass is what I'll get. I need radius in feet. So put in 0.125 slug feet squared, put in the radius of 0.25 feet. I need a 4 slug flywheel or 129 pound flywheel. This is a relatively small engine. Needs a 129 pound flywheel to have a 5% coefficient of fluctuation. That's not realistic. So what you'll find on small engines is they have a quite large coefficient of fluctuation. It might be 20 or 30%. Just that's to have an acceptably sized flywheel, that's what you have to live with. For bigger multi-cylinder engines, it might not be that bad. The book recommends 1 to 5%. That's realistic for some things. For small single-cylinder engines, it's not realistic because the flywheel would have to be absolutely freaking gigantic. So you take this recommended range with a grain of salt. It depends on what you're trying to do with it. We're trying to make it better. So in this case, this would radically reduce the torque ripple, but we have to put a 130-pound flywheel on it to do it. So what happens if the average torque is not 0? So here is a torque output. This is one that you could actually integrate on an exam or homework, something like that. So it's a nice little square wave here. So this is output torque in pound-feet, crank angle in degree. I need to find the area. So first off, I need to find the average torque. That's really the first step if you just encounter this curve, is to find the average torque. So to find the average torque, I integrate this and divide it by the width, right? So integrate this with respect to angle, divide it by 360 degrees. So here's my area total down here. It's 20 times 40, and then, sorry, I kind of erased or covered it up. 20 times 40, and then minus 80 times 80, plus 40 times 100, minus 60 times 120, plus 60 times 60. That gets me the total area with the units of foot-pounds degrees. Divide this number by 360 degrees. That gets me back to pound-feet of torque, and that gets me 14.4, negative 14.4. So that's the average torque output of this device. Remember, I need to integrate TL minus T average. So I need to subtract T average from this curve. So what I need to do is, for every point on this thing, subtract off 14.4. Now I'm subtracting a negative, so that's going to have an effect of shifting this whole curve up 14.4 pound-feet. So that's what I've done here, is I shifted this whole curve up 14.4 pound-feet. Now I need to find all of my zero crossings. This is a plot of TL minus T average. That's what I need to integrate. So I need to find the zero crossings on this graph, and I need to find the area of all of these pulses. So I have to go through and find this area all again because the curve is different now. It's shifted up 14.4. So from A to B, again, now this, I'm not just finding the average. When I'm finding the average, I can use foot-pound degrees, divide by 360 degrees, and it works. Here I'm actually finding work done. So when I integrate this in pound-feet, I have to integrate with respect to radians, not degrees. So crank angle in radians. So I need to turn 80 degrees into radians, 160 into radians, 200. I have to convert all these things into radians and find the area. And it's a giant pain. My recommendation for graphs like this, where it's all in degrees, is find the area of each of these in pound times feet times degree. That's terrible. Pound times feet times degree. And then after you find the area of each of these pulses in pound, feet, degree, then convert degree to radian and get the energy. So if you integrate this in pound, feet, degree, you'll get a number that's off by the conversion factor from degree to radian to my numbers here. So again, it has to be work done. Work is foot-pounds times radians, not foot-pounds times degree. So we got to make sure our units are good here. So I've got here 34.13 foot-pounds, here negative 91.53, here 79.9, here negative 110.54, here 88.04. Now the running sum of this has to end up being 0 because this is TL minus T average, and that has to be 0. The deviation from average has to be 0, or the total energy has to be 0 because I've already offset this curve to the average. So that's a good check. If you did this right, you should end up at 0 for the TL minus T average graph. Then do the sum. So this is A to B, this is A to C, this is A to D, this is A to E, this is A to F. Find the biggest and the smallest. This is the smallest, this is the biggest. The biggest is the minimum angular velocity, the smallest is the maximum. This is where I've delivered the most work and I had to slow down to do it. This is where I've received the most work and I had to speed up to do it. Take the difference between those numbers, again 34.13 plus 88.04. I have a total accumulated energy of 122.17. Okay, so that's my energy for sizing. I've got energy. I want a coefficient of fluctuation of 20%. I've got an average speed of 41.89 radians per second in this case. I get my flywheel inertia from this simple equation here. From that, I can take my geometry, which in this example it was 20% fluctuation, 400 RPM, 12-inch radius, and a disc. So for a disc, I is 1/2 mr squared. I've got a 1-foot radius. I need a less than a slug. I need a 22.4 pound flywheel to get a 20% coefficient of fluctuation in this. So this homework I will put together with balancing. So these homeworks, this homework and then the homework for the material on Friday and Monday, we'll go into, I can't remember which homework 7 I believe, and that will be due next week. So what I want to get you started on this week is the project. This will be due not this Friday but next Friday, so you've got about a week and a half to work on it. This is force analysis for a crank slider. So you'll have to go back a couple lectures. This is back when we were actually meeting in class. The slides will be available on Canvas, and solve this problem. So you've got crank mass, crank length, crank CG location, crank moment of inertia, connecting rod mass, connecting rod length, connecting rod CG location, connecting rod inertia, piston mass, no offset, 45 degree for theta 2, 300 radian per second for omega 2, 0 radians per second for alpha 2. I want you to find the required input torque, that T21, and the pin reactions. That's F21, F23, F34. So how do you do this? So go back to the force analysis slides. There is a big matrix for crank slider force analysis. There's the A, there's the X, and then there's the B. It should be, I think it was an 8x8 for force analysis. So this A matrix here will have a bunch of the position vectors. You'll need to find all those position vectors. This B over here will have things like mass times acceleration or I times alpha. You'll have to calculate those things. Then you'll need to solve this system of equations and unknowns. So I'll put up a tutorial on how to do that in Excel here in a bit, and but otherwise you can use MATLAB, you can use a calculator. Just don't do it by hand. You can use Wolfram Alpha if you're crazy. But any kind of linear system solver will work, but I'll put a tutorial up for how to solve this in Excel if you don't know how to do it. But so that will be force analysis for crank slider. This is a long problem. It's going to take a little bit of time. This is not something you can start on Friday when it's due and get it done unless you're crazy. So I highly recommend you get started on this and ask any questions via email. The best thing to do if you're doing this in a spreadsheet would be to just send me a copy of your spreadsheet if you have questions, and I'll be able to answer it. And if I need to make any other tutorials for this too, if I know about it now, I can put together a quick tutorial on how to solve it. So get started on the project. It'll be due a week from Friday. It'll take quite a bit of time. You'll get another homework assignment that'll be due next Friday too. That'll be for flywheels. So I highly recommend getting started on this week since you don't have another homework. Anyway, that's it for today. Get started on the project, and I'll get exams graded here in the next few days. Get those grades posted on Canvas for you all. So that's it for today. Thank you.